In this video, we are going to discuss about the phases of compiler. We basically have two phases of compilers, namely the analysis phase and synthesis phase. The analysis phase creates an intermediate representation from the given source code, and the synthesis phase creates an equivalent target program from the intermediate representation. Here, a compiler is a software program that converts the high level source code written in a programming language into low level machine code that can be executed by the computer hardware. The process of converting the source code into the machine code involves several phases which are collectively known as the phases of compiler. The typical phases of compiler are lexical analysis, lexical analysis, syntax analysis, semantic analysis, intermediate code generation, code optimization, and finally the code generation. Here, the first phase of the compiler is lexical analysis, also known as scanning. In this phase, it is used to read the source code and breaks it into a stream of tokens, which are basic units of the programming languages. The tokens are then passed on to the next phase for further processing. The next phase is syntax analysis phase. It is the second phase of the compiler. It is also known as parsing. In this phase, it takes the stream of token as an input, and that phase is produced by the lexical analysis phase. And in this phase, it checks whether they conform to the grammar of the programming language. And the output of this phase is usually a parse tree or a syntax tree, which is also known as abstract syntax tree. The third phase of the compiler is semantic analysis. In this phase, it is used to check whether the code is semantically correct. That is, whether it conforms to the language's type, the system, and the other semantic rules. In this stage, the compiler checks the meaning of the source code to ensure that it makes sense. The compiler also checks for the other semantic errors such as undeclared variables and incorrect function calls. The fourth phase of the compiler is intermediate code generation. In this phase, it generates an intermediate representation of the source code that can be easily translated into machine code. The fifth phase of the compiler is code optimization. In this phase, it applies various optimization techniques to the intermediate code to improve the performance of the generated machine code. And the final one is code generation. This phase takes the optimized intermediate code and generates the actual machine code that can be executed by the target hardware, which means where it used to makes the code as an optimization code. It combines the code which is having common sub expressions and common values in the same table that are optimized in this phase. Here, each phase of the compiler plays a crucial role in translating the codes. So here the phases of a compiler is enter all the data in the symbol table. Now we are going to see what is symbol table. Symbol table is nothing but a data structure being used and maintained by the compiler, and consisting of all identifier names along with its types. It helps the compiler to function smoothly by finding the identifier quickly. The compiler has two modules, namely the front end and the back end. Front end constitutes the lexical analyzer, semantic analyzer, syntax analyzer, and intermediate code generator. And the rest are assembled to the form of the back end. So first we are going to discuss about the lexical analyzer. It is also known as scanner. It takes the output of the preprocessor as the input, which is in pure high level language. It reads the character from the source program and groups them into lexemes. Each lexemes corresponds to a token. Tokens are defined by a regular expression which are understood by the lexical analyzer. It also removes lexical errors, white space, comments, etc. Next one is syntax analyzer. Now we are going to discuss about the syntax analyzer. It's sometimes called a processor. It takes all the tokens one by one and uses context-free grammar to construct the parse tree. It constructs the parse tree. The parse tree is also known as derivation tree. Why we are constructing the parse tree means here the parse tree is usually constructed to check for ambiguity in the given grammar. There are certain rules associated with the derivation tree, that are any identifier is an expression, any number can be called an expression. The parse tree can be compressed to form a syntax tree. It is also used to find the syntax error inside the program. Syntax error can be detected at this level if the input is not in accordance with the grammar. Next phase is semantical analyzer. In the semantic analyzer, it takes the parse tree as an input and gives the output as an semantically verified parse tree. Where it verifies the parse tree whether it's meaningful or not. It furthermore produces a verified parse tree for label checking and type checking and flow control checking. Next one is intermediate code generator. It generates the intermediate code, which is a form that can be readily executed by a machine. We have many popular intermediate codes. For example, we can say 3 address codes. Here the intermediate code is converted to machine language using the last two phases, which are platform dependent. If we wanted to build a new compiler, we don't need to build it from scratch. We can take the intermediate code from the already existing compiler and build the last two parts. Next one is code optimizer. Here we are mentioning that one in the machine independent code optimization. It takes the intermediate representation as an input and produce the output as intermediate representation, where it transforms the code so that it consumes fewer resources and produces more speed. The meaning of the code being transformed is not altered. Here the optimization can be categorized into two types. The first one is machine dependent and the second one is machine independent. Okay, next one is code generator. Code generation takes an input as an intermediate representation and gives the output as a target machine code. Where we can say the target machine code as a target code generator also, code generator. The main purpose of the target code generator is to write a code that the machine can understand and also register allocation, instruction selection, etc. The output is dependent on the types of assembler. This is the final stage of compilation. The optimized code is furtherly converted into relocatable machine code to perform the input to the linker and loader. Now let us discuss about the example of compiler. Here the example we consider the statement position is equal. We consider the assignment statement position equal to initial plus rate star 60. The character in this assignment could be grouped into the following lexemes and mapped into the and we can map the mapped into the following tokens passed on to the syntax analyzer. First one is in this assignment taken, we can first take a position is a lexeme that would be mapped into a token id comma 1. In this diagram you can see position is replaced as id comma 1, where id is an abstract symbol standing for identifier. We can say this one as a symbol table entry identifier, and also the one points to the symbol table entry for position. The symbol table entry for identifier holds information about the identifier such as its name and type, and also the assignment symbol is equal to symbol. After the position we can see the symbol, assignment symbol equal to. It is a lexeme that is mapped into the token equal. So can you see the difference from lexical analyzer to output of the lexical analyzer? The equal is mapped into the equal symbol, and then again we can see initial is a lexeme that is mapped into the token id comma 2, where 2 points to the symbol table entry for initial. Next one is the operator plus. It is a lexeme that is mapped into the token also plus, where we cannot see any changes in the operators. Whenever we start processing from lexical analyzer to syntax analyzer. And also next one is the value rate. That is also a lexeme that is mapped into the token id comma 3, where 3 points to the symbol label entry for rate. Next one is the operator multiplication. It is also a lexeme that is mapped into the token star. Next one is the value 60. It is also a lexeme that is mapped into the token 60, where blanks separating the lexemes would be discarded by the lexical analyzer. The presentation of this assignment statement, position equal to initial plus rate into 60 after lexical analysis as the sequence of tokens. Can you see in the you can also see in the particular PPT, id comma 1 is equal to id comma 2 plus id comma 3 into 60. Next one is the particular input is again sent to the again taken as an input to the syntax analyzer, and it produces the tree format as an output. In this tree it has an interior node labeled with id 3 as its left child and the integer 60 as its right child. The node id comma 3 represents the identifier rate. The node id comma 3 represents the identifier rate. The node star is here. The node star here, can you see the node star? That makes it explicit that we must first multiply the value of rate by 60. Then the node labeled plus indicates that we must add the result of this multiplication value of initial the root of the tree labeled is equal to, that indicates that we must store the result of this addition into the location for the identifier position. Next one is, now we are sending the parse tree as an input to the semantic analyzer. So in our example, suppose that position initial and rate have been declared to be floating point numbers, and that the lexeme 60 by itself forms an integer. The semantic analyzer discovers the operator multiplication is applied to a floating point number, rate and an integer 60. In this case, the integer may be converted into a floating point number. Can you see the figure? notice that the output of the semantical analyzer has an extra node for the operator into float, which explicitly converts its integer argument into a floating point number. In the left corner, can you see the symbol table? The symbol table consists of position, initial and rate, and its entry values and along with its position. So this is what we are having in a symbol table entry. Next part is intermediate code generation. In our example, in an intermediate representation, I used this 3 address code, which consists of sequence of assembly like instruction with 3 operands per instruction, because 3 address code only accepts whenever the expression having only 3 addresses, or the maximum of address should be 3. So in this intermediate code generation, it consists of 2 important properties. It should be simple and easy to produce. It should be easy to translate into target machine code. Next one is code optimization. In the code optimization, the phase attempts to improve the intermediate code so that better target code will result. In our example, the optimized code is T1 is equal to ID3 into 60.0 and then ID1 is equal to ID2 plus T1, where we are changing the value of 60 into 60.0 in T1, 60.0 and make the next expression T2 as T1 and directly assign the value T1 as a 60.0 in the code optimizer. And then next one is ID1 where the T3 value is assigned as ID1. We are going to add 2 values, that is ID2 and T1 for an code optimization. Here it removes all the common sub expressions and make the other properties for optimizing that particular code. And then finally we are going to generate the particular target code using code generator. It takes an input as an intermediate representation of the source program and maps it into the target language. If the target language is assembly language, this phase generate assembly code as output. In our example, code generated is the first operand of each instruction. The first operand of each instruction specifies a destination where the F in each instruction tells us that it deals with floating point numbers. The above code loads the contents of address ID3 into register R2 and then multiplies it with floating point constant 60.0, where the hash signifies that 60.0 is to be treated as an intermediate constant. And also the third instruction moves ID2 into register 1, which means we are loading the ID2 value into the register 1. And then fourth instruction, where we are adding the values R1 and R2 and store the value in an ID1. So here we are finally assigning the value R1 is equal to ID1. This is what we are going to do in our example. And finally, at last, we are going to see the topic symbol table management in phases of compiler. It is an essential function of a compiler. It is used to record the variable names used in the source program and also collect information about the various attributes of each name. For example, by value or by reference, the method of passing each argument and the type returned, and in case of procedure names such as the number and types of its arguments, these attributes provide information about the storage allocations. Here the data structure is used, and that data structure, the simple table is also a data structure. Here the data structure should be designed to allow the compiler to find the record for each name quickly and to store or retrieve data from that record quickly. Next one is error detection and reporting. In this phases of compiler, each phase can encounter errors. However, after detecting an error, a phase must somehow deal with that error. So the compilation can proceed, allowing further errors in the source program to be detected. We can also find the first error is not helpful one. Then the process of compilation is split up into two phases for finding out the errors. Thank you.